So today we're going to talk about iterators and ranges and exploring library designs for traversal and the way that different languages solve this particular problem. But first, a little bit about me. I am a C++ software developer at Jump Trading. I've been there since 2014. Jump is a global trading firm committed to world-class research and development. Our focus is to be the best trading firm in the world across all asset classes and all time horizons. We design, develop, and deploy technologies that are at the leading edges of the field. We also fund startups across industries and partner with leading global research organizations and universities to solve a wide variety of problems. And we're always looking to add new and talented engineers to a variety of teams, so feel free to check out our LinkedIn page and reach out if you have any questions. Outside of Jump, I've also been a participant in the C++ Standards Committee since 2016. And you might know me from a bunch of different language features in C++20, like spaceship, init capture, pack expansion, explicit bool, conditionally trivial special member functions, and hopefully coming soon to a C++ near you, deducing this and if const eval are the language features I've been working on. I've also been involved in a whole bunch of ranges papers, not so much for C++20, but hopefully in the next standard to come, hence my interest in this particular topic. And this is Hannah. Hannah is my life mascot, and she is my avatar across social media, where you can check out my blog, or you can find me on Twitter at Revzin, or you can find me on StackOverflow, where my handle is just Barry. Outside of the C++ world, I'm an avid swim fan, and I write a lot of data articles for SwimSwam, which is the premier swimming news organization. And also on the side, I do analysis for the DC Trident professional swim team. Which is a lot of fun. So if you catch me talking a lot about swimming, that's kind of my thing. All right, so let's dive in. So we have some sequence. It could be a contiguous sequence of integers. It could be some kind of like disjointed contiguous sequence, like something like a rope or a deck. It might be a sequence that has embedded nulls in it, like an open address hash table or a colony where we have to skip elements. It could be a linked list. It could be a binary tree. It could be a linear chained hash table, or it could even be a generator that creates elements on demand whenever we ask it for one. But whatever the kind of sequence is, we need some kind of uniform access pattern, because it'd be incredibly unwieldy if for every kind of sequence that we have to deal with, we have to write bespoke code to even do the basics like iterating over it to, let's say, print all the elements. And when you look at the kinds of things that you need to do for like what this uniform access pattern might look like, you find out that there are some basis operations that we certainly need to cover, regardless of the way that we choose to do this. The first basis operation is read. Of course, we're not going to get very far if we never get any ability to actually look at what any of the elements are. So we need to start there. We need some way to advance, because if all we can do is read the first element over and over again, that's not very productive. So we need a way to actually go through the sequence, reading our elements, and we need a way to find out when we're done. Because we need a way to eventually terminate whatever loop or whatever algorithm that we're doing. Importantly, these need not be three distinct operations, but they all need to exist in some form or other. And we're going to walk through a bunch of different ways that various languages address these three operations. And so we'll start with C++. The C++ iterator-pair model, which has been around for a very long time, and which I suspect a lot of people in this conference are going to be pretty familiar with, but I think it'd be worth kind of just going through it real quick as a refresher. So in the C++ iterator model, we have, as the name suggests, a pair of iterators, one that points to the first element and one that points one past the last element. And the things we can do with these iterators are we can advance them using increment. If we're bidirectional, we can decrement them. And we can even, if the end iterator is actually an iterator, we can decrement the end iterator as well. Importantly, if we have a bidirectional range, we can move either the begin or the end iterator in either direction, which is quite nice. And if we have a random access iterator, then we can jump by an arbitrary amount as well. We don't have to just increment repeatedly. And this is basically at a high level, this is what the iterator model looks like. And so these operations map very cleanly onto these basis functions that I just mentioned. Read is spelled dereference, advance is spelled pre-increment, and done actually requires two different objects, right? An iterator by itself doesn't know whether or not it's done. We need to compare it to something. With the new model, we compare to what's called a sentinel, or maybe also an iterator, but we need some other thing. So we always require 2 elements. And so if we look at what the range structure looks like in C++20 anyway, we get like this. This is like the bare minimum range that we might have. And so we see here our iterator has a read, which is our dereference operator, which is const, which returns some kind of reference. We have our advanced functions, which are our pre-increment and post-increment, which should better be semantically equivalent. And we have our done operations, right? So if you have a forward or better iterator, it needs to be quality comparable with the same type. But if we also have a sentinel, we need the iterator to be comparable with the sentinel as well. And so when we use these types, when we use our range with our iterator and our sentinel, we consume the iterator as we go, right? So we mutate the iterator using the increment operation until it eventually is done, until it eventually is equal to whatever the end state is. But we don't consume either the range or the sentinel. They kind of stay hanging around. So if you kind of look at just like this basic structure, there's a lot going on here, right? If we just like go through and count, we'll see that we have 1, 2, 3 different types that we have to reason about. And we have what, 1, 2, 3, 4, 5, 6, 7, 8, 9 functions that we may have to implement. So that's kind of, there's a lot, right? There's a lot in this model. And when we look at kind of the simplest algorithm that we might do with the range is that just iterate through it and print every element. We see kind of our basis operations in action. We see our done at the beginning of the loop as our loop condition. And then when we enter the loop, we read every element in order to print it. And then lastly, we advance to get to the next element, right? So this is the basics of C++ range, which again, most people here are going to be familiar with. So let's kind of move on to more complicated stuff. And let's talk about adapting ranges. All right, so once we have ranges, we might want to make other kinds of ranges on top of those ranges. And the 2 range adapters that come up most often and that people are going to be most familiar with are transform and filter. So applying a function to every element in a range, or just reducing the set of elements in a range to those that match some kind of predicate. All right, so let's go through and implement transform in C++. So transform view, of course, has an underlying view that it holds onto, the thing that we're transforming, and it has our unary invocable, the function that we're applying for every element to the underlying view. Although C++ calls this transform, but pretty much every other language calls this map. So let's actually just go ahead and call it map for consistency for the rest of the talk, right? So we're implementing map view now. And so we have our begin, which returns an iterator that we'll get to, and we have an end that returns a sentinel. Okay, so there's a starting point. But that's not quite right, because we also need another overload of end. If the underlying range is what's called a common range, which means begin and end return the same type, we want to preserve that behavior for our range adapter as well. So if V is a common range, we want map view of V to also be a common range. And this is especially important once we get to bidirectional, because if you can walk backwards from the end for the underlying range, we want to preserve that functionality in the map view case as well. Although for the purposes of this talk, I'm really only going to be focusing on forward for simplicity. But for completeness, it's important to present that here. But even this isn't quite enough because all these 3 functions are non-const. And we also have to deal with the fact that, well, what if the map view itself is const? Can I iterate over that? And those conditions are going to be slightly different. So what you end up is, well, the iterator and sentinel types aren't necessarily just 2 types. They're both templates. And we actually have a different iterator based on whether we're const or not. First, because the view itself are going to be const or not. And while typically views we think of as being shallow const, that isn't necessarily the case. And so we have to handle these cases differently. So we have really 6 functions to do begin and end for us, depending on whether or not we're const and whether or not the underlying range is common. All right. Although these functions themselves are pretty easy, they're all just like return whatever, and I'm not even going to show that here. But let's get into the iterator, which is actually kind of interesting. So to start with, the iterator has to hold on to its underlying iterator, right? The iterator that it's adapting. We need this thing because that's how we get access to the underlying range. And we also need access to the parent to get the function that we're going to apply to every element. And so we have our bunch of aliases that we need to provide, where the reference type in this case is going to be the result of invoking the function on the reference of the underlying base. And the value type is just removing the constant reference qualifiers from that. And of course, we need to be able to construct the iterator, which typically is going to be constructible from either the parent in an underlying iterator in the usual case, or const iterator needs to be constructible from iterator. So we need to make sure that we get that right, and along with all those constraints. But then we get to the real meat of the iterator, which is the really important functions. So we have our read operation, which is based on just invoking our function on the result of reading the underlying iterator. So we implement our read in terms of the underlying read. Advance is simply advancing the underlying iterator. There isn't anything else we have to do there. And done is likewise also just comparing the underlying iterators there. There's nothing special that map has to do in this case. All right, so let's kind of like collapse this code a bit so that we can take a little bit more space. And then let's talk about the sentinel that we have to add. So the complexity of the sentinel is that regardless if it's a const or non-const sentinel, it has to potentially be comparable to either the const or the non-const iterator. And so the equality operator here is a little bit involved, right? We have it itself is a template. It has this requires clause attached to it. Although the body is just like, we're comparing the underlying things. So nothing here is necessarily complex, except for maybe the constraint on the sentinel's comparison operator. But there's kind of a lot that we have to do. And it looks a little bit daunting, especially if we kind of stick it all together on one screen. And if we count all the things that we need to do, well, we have 1, 2, 3, 4, 5 types. And maybe you can quibble with that, like, well, iterator and sentinel should really only count as one each. But the fact that we need to care about the interaction between iterator and const iterator, sentinel, const sentinel, I think it's pretty fair to count them up to 5. And if we go ahead and start counting all the functions that we have to write, there's a lot, right? There's 18 functions that we have to write. And none of them are complicated. Nearly all of them are single expressions in the body, but it's tedious, right? And especially because the only really important part of map view is this invoke that we need to do, right? Like this is the semantics of map view, is that we're invoking this function on every element in the underlying range, but we have to write all the stuff around that just to convey that semantic. Okay, so that's map. Let's talk about filter. Filters has this other problem. So with map, we have this one-to-one correspondence with the elements of the mapped view from the elements of the underlying view that we're mapping. But that's not true for filter. In particular, we don't even necessarily know which element is going to end up being the first element, right? So how do you make begin work? Which actual iterator do you return? And know that we have this additional requirement on views that begin has to be amortized constant time. So we can't just do a search every time you call begin. That's going to be pretty important for algorithmic complexity later on. So the only way we can really do that is we stash an iterator. So if we haven't done this stashing first, like the first time we call begin, we go ahead and look for it. We use findIf, of course, and that lets us return the right iterator that we need. And then so subsequent invocations of begin let us just return what we've already stashed. And this is kind of a problem because we have to do this mutating operation on begin, which prevents us from being able to make filter view considerable. Because the standard library provides a strong guarantee that any function marked const doesn't introduce a data race. Like these things are going to be thread safe. So the only way to do that for filter view would be to like insert a mutex or something, and that becomes super expensive. So the choice that the standard library makes is to simply provide non-const begin and end for ranges like filter view. But we still do need the end to handle the common range case for the same reasons that we wanted it for filter view. So if we go forward for the iterator, we have the same kind of structure. So we have the underlying iterator that we need to look at and our parent to get the predicate that we need to use. In this case, it's a little bit simpler because we don't have to do this maybe constants because iterator is no longer a template. And we have the same set of aliases with the same constructor. That's kind of boring. And then we go through and again, we look at like the meat of the operations are our basis operations for how we actually do adapting. And here read is completely transparent because filter doesn't modify the way that read works. It simply defers to the underlying iterator. The complexity comes from advance because when you advance an iterator, we then have to look for the next iterator to match. And here it's important to get access to the parent's end because of course we need to know when to stop searching. but otherwise it's just a simple find if. And likewise, done is simply comparing the underlying iterators. No complexity there. If we collapse this again and add our sentinel, it looks exactly the same as we had before, just a little bit simpler because it's no longer a template. And the comparison for the iterator is just comparing the underlying sentinel to the underlying iterator. Putting it all together, it's a little bit less code overall, simply because these things aren't templates anymore. But there's still a lot, right? So we have 1, 2, 3 types, and if we count up all our functions, there's a lot of code. 13 different functions. And this is a little bit more complicated than map because we have to do this caching operation on the begin iterator. We have to do this algorithm for advance. It's not just simply ++, but it's still a lot of extra code that needs to be written when really the important parts of filter view is basically this find if operation, which unfortunately has to be duplicated. So we can get the functionality we want, but there's a lot we have to write to get there. So let's move up to D. The D ranges model was introduced by Andrei Alexandrescu, as far as I know, in a 2009 talk entitled "Iterators Must Go." And I imagine a lot of people here might not be familiar with the D ranges model, so it's definitely worth going over what that looks like. So in D, instead of having a pair of iterators that denotes a range, we have a single object that is the whole range. And in D, a range is more analogous to what in C++ we would call a view. So it's not owning, it's a lightweight thing that we can just pass around. And the operations that we have on it are like pop front. So pop front here does not destroy the first element. It just moves the beginning of the range such that it no longer includes it. And so we can pop front again, and now we only have 4 elements in our range. If our range is bidirectional, we also have pop back to remove the last element. But notably, there's no unpop front or unpop back. Once we popped an element on one side or the other, there's no way to recover it. Ranges can only shrink in size in the D model. And if you think about it, this makes sense. The range knows that it can shrink. That's a perfectly safe operation, but it doesn't really know like where the real bounds are to the extent that they're all real bounds. And so those operations simply are not offered. If the range is random access, it also supports a slice operation. So you can pick anywhere from the beginning to anywhere at the end, as long as you're within the original bounds, and just produce a new range out of it. And so these operations that D offers in its model map very closely onto the basis operations that I introduced, the read, the advance, and the done. And they also map very closely onto the C++ operations that we provide. The primary difference here is that done, the range knows itself when it's empty, unlike in C++ where we need a second iterator or a sentinel to really know that when we're done. And so if we were to implement the D range structure in C++, it would look something like this, right? We still have these aliases that we need for the same kinds of reasons. We still have some notion of range category, but we have these 3 functions. We have read, we have advance, and we have done. They're just spelled, a little bit differently. And importantly, the range here is going to be consumed. Like when you use the range in an algorithm, you're repeatedly calling pop front until you run out of elements, and then we have an empty range. We just discard it, we throw it away, we move on with our lives. This is the thing that's consumed. So we only have one type, just the range, and we only have these 3 operations: the front, the pop front, and the empty. So there's a lot less code, and it's very straightforward to map C++ iterator pairs onto the D model. Given any input iterator and any sentinel for that iterator, we can easily produce a D range out of those pairs of elements, right? So front just dereferences first, pop front increments first, and empty just compares the iterator and the sentinel for equality. And this is now a perfectly valid D range. So if we look at our print all example, the loop basically looks the same because these models are very close together. It's just that the spelling of done is now not r.empty instead of an equality comparison. The read is just spelled front instead of a star it, and the advance is spelled slightly differently. But the overall approach is quite similar. So let's go ahead and look at what it would look like to adapt ranges in D. So how do we implement map and filter in this slightly different model? So we start out kind of the same. In order to map a range, we need to hold on to the underlying range. We need to hold on to the function. We have our same set of aliases where reference is still the invoke result of the function on the underlying reference of the range. This is still the same. But the only real difference is when we implement the meat of this range, we get our front that's implemented in terms of front, we get our pop front that's implemented in terms of the underlying pop front, and we get our empty that simply is implemented in terms of the underlying empty. That's it. This is basically the entire implementation of map in D. And so as you can see, all we have is one type. And we really just have 1, 2, 3, 4 functions that we have to implement. And we can quibble to what extent the constructor really counts. But of course, that's a lot less code that we have to write. And there's a lot less boilerplate around this invoke that we have to do in order to provide this mapping functionality. So let's move on to filter. Filter has the same problem indeed that it had in C++, which is how do we make sure that we get the first element correct? But D has a slightly bigger problem here. In C++, we have one entry point. The range has a begin, and begin has to provide that iterator. So we know that whatever functionality we have to do to make sure that we get the first element, it just goes into the begin. That's the only place that it can go, really. But in D, we have 3 entry points, right? We have pop, front, and empty, and we don't know which one of them the user is going to call. So we have to make sure that all 3 of those functions can correctly handle finding the first element. And so the way that the D standard library does this is it introduces this operation called priming. And so a filter range starts out not primed, and we have this operation to prime it, which is if we haven't primed yet, go ahead and look for the first element in the range that satisfies this predicate, and then mark ourselves as primed. And of course, we want to avoid using raw loops like this, so we could replace this with a find if. Notably, in C++, algorithms return iterators, but in D, we don't have iterators, so algorithms return ranges. In this case, find if returns a range starting from the first element that satisfies the predicate. And we'll get more into algorithms shortly. So now that we have prime, which ensures that the first element in the underlying range satisfies the predicate, or it's empty, then we go ahead and we can implement all 3 of our operations using prime. And this might be more obvious if I shift it over a bit. So you can see that all 3 functions, the first thing that they do is call prime to ensure that the first element is correct. And once we do that, they basically just implement themselves, right? So front simply defers to the underlying ranges front implementation, empty defers to the underlying ranges empty implementation, and pop front first has to do a pop front, and then it has to do another find if to advance the next element properly. And so while filter in D is a little bit more complicated than map in D, it's still just one type, and it's still just 5 functions that we have to write, which is a lot less code overall compared to the C++ model. And let's actually decide and have a bonus slide on C#. So C#'s model, it calls it IEnumerator, and it's also quite similar. It still has a read operation, which it spells current. Actually, in C#, current is a property, but we don't have properties in C++, so I'm just going to add parentheses and hope that no one minds too much. But rather than having advanced and done as distinct operations as they are in C++ and D, we actually combine them, and we have a single operation which is called move next. But here it's a little bit different, where in C++ and D we start out pointing to the first element. In C# we actually start out pointing before the first element. So if we have our same print all loop, we actually have to advance first and then check if we're done, and only then do we do our read. So it's in a slightly different order, but I would consider these models to be very similar. C# is slightly more different than C++ and D, but they all seem to be like in the same kind of family. And I would call these the reading languages. And what these languages have in common is that read is a distinct idempotent function. And what I mean by that is it's distinct, it's a separate function that exists. And if you call read repeatedly, you will always get the same element over and over again. It may not be free to get that element over and over again, but you always get the same element. And this has one very interesting downside that a lot of people run into very quickly when they do any kind of ranged action. And that is this example. So let's say we have some range and we're mapping some operation onto it. And I'm not going to tell you what the operation does, but it does something. And then we're filtering. And once we do that mapping in the filter, we're going to iterate over the range and just print all the elements. And the question is, how many times is some operation invoked at the end of this implementation? And the answer is like you don't really know, right? It's not obvious. I'm not telling you if some operation preserves the parity or does something. Maybe some operation just returns 1 all the time. So let's kind of go through and see if we can provide a more precise answer to this question. Like, how many times are we really invoking this function? Like, maybe it's expensive and we don't want to invoke this function more times than we strictly need to. So if we go back to the C++ implementation, so here's what read looks like for the iterator and what read and advance look like for filter. And so what happens is when we read the filter iterator, that reads through the map iterator, which has to invoke a function, right? So every time that we actually read an element out of the resulting filter view, we have to invoke this function. But the issue is when we advance the filter iterator, we have to find where we're stopping. And when we're stopping, we have to invoke our underlying iterator to see what the value is there. And that also reads through the underlying map iterator, which also invokes the function. So every time we advance, we get to some functions, some element in the range, we invoke the function. And if that satisfies the predicate, then we have to read through that iterator again, which invokes that function again. So what we end up with, elements that satisfy the predicate are actually transformed twice, while elements that don't satisfy the predicate are only transformed once. And now, so you might ask, well, is this a C++ problem? What did we mess up? Is there something we can do? So let's look at D. What does D look like for here? Well, this actually looks very similar, right? When we read through the filter range, that reads through the map range, and that has to invoke a function. But when we advance the filter range, that has to read through the map range and still invoke the function again. We have exactly the same problem. If we map and then filter in D, we still invoke the function twice for every element that satisfies the predicate. And this is exactly the same thing is true in C#, which has exactly the same structure, right? Because when we do current on filter, that has to invoke, that goes through current on map, which has to invoke the function. And when we do move next on filter, that again has to invoke the function through the map iterator again. So this kind of problem is inherent for all of the reading languages, really. But let's kind of go back. So I showed that the D model was simpler, right? Map and filter both have fewer types, fewer functions in D than in C++. And the D model has been around for a very long time at this point. So the question might be, well, why don't we just copy it, right? Like, why did C++20 ranges continue the iterator-pair model instead of simply copying the D model if it's so much simpler? So let's look at findIf. I mentioned earlier that findIf in D has to return a range, while in C++ it returns an iterator. But otherwise, these two algorithms are very equivalent, right? Like the code basically looks the same. Some of the spelling of the operations is different, but these are recognizably equivalent. And there's no particular reason to say that one is necessarily better than the other. But let's consider a slight variation of this. Let's say instead of I want the first element that satisfies a predicate, I want the range until the first element that satisfies a predicate. So how do I write that algorithm? In C++, well, we just wrote findIf, and we can just use it to get that iterator, and then on the fly, just construct a new range from first to that iterator, and we're done. And this is pretty clearly just correct by construction. Our algorithms compose very nicely together. But in D, that's not really the case. So if I do findIf in D, okay, so I get the range starting from that element, but what do I do with it at that point? I can't just like invert it. There's no clear way for me to get the elements before that. I can't back up R. There's no way to do that. I can't recover elements. So I'm kind of just stuck. So one thing I can do is I can write my own range. I can produce until range, where until range is a lazy range that produces all the elements until this predicate is satisfied. And indeed, this is fairly straightforward to do. And then I can return an instance of that. So this is actually slightly different because my D implementation here is completely lazy, whereas my C++ implementation is actually eager. But this is still useful, right? And in fact, this until range here might be more recognizable to people as take while range, which is a separate range adapter that's quite useful. So okay, well that's kind of nice. But there's also a very different way that we could do this. Instead of implementing until in terms of take while, we could instead implement it in terms of take. All right, so let's kind of sidestep and look at take real quick. Take is a range adapter that, as the name suggests, it takes the first n elements, or rather up to the first n elements. So as you can see, the empty check here our range is empty when either our counter hits 0, which gets decremented in hot front, or the underlying range is empty, whichever one happens first. And we can use take range to implement until a slightly different way. So whereas in C++, what we did is we looked for the first iterator whose underlying element satisfied the predicate. Instead, what we're going to do is just count. So we have our counter n, and we increment it as we're going through the range. And once we get done with this loop, n is going to refer to the number of elements that are before the first element that satisfies this predicate. And so we take that many elements. And indeed, we can do it a little bit better than this, right? So if you look at take, the condition for empty is either the counter hits 0 or the underlying range is empty. And that needs to handle the case where we try to take 100 elements out of a range that happens to only have 50. But we know that that's not the case here, right? We've already counted n elements out of this range. So we know for sure that the range has at least n elements. So we can reduce the performance cost here by using a slightly different range adapter, which D calls take exactly. So again, as the name suggests, take exactly range takes exactly n elements and is simply undefined behavior if the range happens to have fewer than that. So we can implement our until in terms of that. So we count how many elements we need to take, and then we take exactly that many elements. And we can refactor this a little bit by putting that into an algorithm. And we call that algorithm position. So position takes a range and a predicate and counts how many elements before the first element satisfies that predicate, and then we take exactly that many elements. So if I bring back the C++ implementation here, these look very similar, right? If you look at them, particularly the boxes here in until, right? In C++, we're returning a subrange from first to the result of find if, and in D, we're returning take exactly range from range until the position. So again, these approaches are very similar to each other, but the difference is in C++, I just have one algorithm. I wrote find if and I just use it. But in D, we had to write all this other stuff. And in particular, in D, we end up relying on indices a lot more because in D, we don't have iterators. But iterators are useful. There's a surprising number of places that they come up, and it's nice to have them. So let's look at another example, and let's talk about splitting. So let's say I have a range. In this case, it has 7 elements in it. And what I want to do is I want to search for some sequence in that range. And in C++, that algorithm is called search. And let's say I'm searching for DE. And the result of this algorithm is it gives me 2 more iterators. So I already had first and last to start with. And the result of search gives me mid.begin and mid.end. And the very important aspect of the C++ iterator pair model is that any pair of iterators from the original range itself can be used to denote a valid range. So in this case, I have 4 iterators. I can pick any 2 iterators to produce a new range. So I really have 6 ranges that I can deal with. So let's say I do this search, and I want to get the pieces of the original range back, right? So let's say what I really want to do is I want to get these 3 pieces as separate entities back. So once I get search, I can just take the pairs of iterators that I need, combine them together with subrange, and return that as a tuple. And that's pretty easy to do. We don't have find split in the C++ standard library, but you probably don't even need it. Once you've used search, it's just easy to put together the things you need. But maybe I want a slightly different set of these pieces, right? So maybe I want the part that I searched for to be attached to the next part. Well, that's just a matter of picking a different set of iterators that I'm joining together to make subranges. Again, just a 4-line function. And maybe I want this searched subrange to be attached to the first range. So again, it's just picking a different set of pairs to join together to return as a tuple. So what you see in these 3 different algorithms is that the implementation is basically the same, and they're all just built on top of search. Search is the workhorse, and everything else is kind of trivial and not very interesting. But that's really not the case in D. So this is the implementation of find split in D. And I don't really expect anyone to read this. This font is kind of small. But what's interesting is D also has find split before as an algorithm. And as you can see, it's also quite long and very, very close together to the implementation of find split. And they also have find split after, which again is very, very close to the implementation of find split before, which is itself very, very close to the implementation of find split. And there's just not a lot of room for reusing the same functionality there, because it turns out that iterators are useful. And so D has to fall back to relying on indices a lot, which doesn't lend itself as nicely to code reuse. But it's important to kind of point out this particular aspect, to kind of just zoom into it, and then kind of strip away the type specification that we're not really interested in. So this is kind of the happy case in the D algorithm. If what we're splitting on is a random access range that is sized and is sliceable, then we have this actually very simple implementation here. And this very simple implementation is quite reminiscent of what we had in C++. In particular, haystack from 0 to pos is very much the range's subrange from first to mid, not end. And haystack from pos to the end of the haystack is, again, range's subrange from mid, not end to last. So in this particular case, in our happy case, when we can use indices, the D and C++ implementations are basically the same. They're basically identical. But as soon as we're not in that happy case and we want to deal with bidirectional or maybe even only forward iterators, we have to write this bespoke thing every time. So it ends up being more work for us. So if I were to really ultimately compare C++ and D, and I were to put them on a chart, I would kind of graph it something like this. So this curve here is kind of what I would consider the efficient frontier between complexity and functionality. Now, I don't think anyone would really argue with me that the C++ model is more complex than the D model, so I'm not going to really spend too much time on that. But I do want to talk about what I mean by functionality here, because what I don't mean is just the scope of algorithms that the standard library provides, since especially when it comes to C++ range adapters, the standard library doesn't really have that many yet. And I don't necessarily mean like various language features that make writing code using these models better. So D, for instance, has unified function call syntax, and when we talk about Rust, Rust has traits which let you write code in a much nicer way. What I mean by functionality is just like the breadth of functions that you can write, the breadth of algorithms that you can produce, and how composable they are. And in that sense, I think C++ is the clear winner. It does provide more things, and it's easier to write and compose a lot of these algorithms than it is in D. But we do pay the cost for that. They are more complex. But it's a trade-off. I don't think it's easy to say that one is strictly superior to the other. And they are very close. So once you learn one model, it's very easy to kind of understand the other. So let's talk about Rust. Rust is very different from C++ and D as far as their approach to solving this problem goes. And so for those of you not familiar with Rust, have you thought about just rewriting it in Rust? So if we have our sequence, the Rust iterator model really provides one operation, and that operation is called next. And so we get next, and that gives us the next value, which is in this case 483, and that's it. We lose our ability to even access the 483 again. We use the value that we have, and that's it. If we don't do all the things that we needed to do with it, it's gone, right? Like once we get the next element, once we get our 556, we have no way of going back and getting the 483 again. It's simply not possible. Rust also supports double-ended iterators, which have a next back method, which works the same way. Like once we get this value at the end, that's it. We use it or not, but we have no way of recovering it again. And so if we go back to our table, we see that this is basically all three operations stuck together. What next does is it advances ahead. It checks if we're done and maybe gives us a value or not. And that value that it gives us is the way that we read through the sequence. So rather than having three or maybe two different functions that adhere to our basis operations, Rust really only gives us one. We just have the one function. So the basic iterator structure in Rust just looks like this. Next is our one-stop shop for everything, advance, read, and done. And we have a single type that is consumed as we iterate through it. So just for consistency, to count things up, we have one type, we have one function. And there's not that much less that is possible to do than just to have one of each. Now, it's important to point out that this optional that I'm using here has a capital O, because this is not std optional. It is very important in this model that we be able to support optional references. And std optional does not support optional references, and so it's simply unusable in this problem space. there's a lot of talk that I've seen about how, like, oh, optional doesn't need to support references. Isn't optional tref really a pointer? Why don't you just use t star? Why don't you just use optional maybe reference wrapper t? And none of those really are solutions. Like the whole point of this talk is we need to provide a uniform iteration mechanism. And if every iterator simply gives you an optional t, that's uniform. You always get an optional t. And there's no other way to really provide a uniform mechanism. Having this function provide very different kinds of things, like either optional t or t star, or optional t or optional reference wrapper t, those are very different types with very different interfaces, with different semantics. And that's just not a good solution to this problem. So for doing something like this, you really do need optional references. So in this case, capital O. So given a C++ iterator pair, or a forward iterator and a sentinel for it, we can produce a Rust iterator, again, pretty simply. Since what next has to do is, if we have an element, so if first is not equal to last, then we return that element. We read through the iterator and return that reference, post-incrementing in this case, since we need to handle the advanced operation as well. And once we're done, we just return null opt. Handling input iterators is a little bit more complicated because we need to make sure that we advance correctly, since we can't post-increment. But it still maps very cleanly onto the Rust iterator model. So given a C++ iterator pair, you can always produce a Rust iterator, but that is decidedly not true in the other direction. Given a Rust iterator, you cannot, in general, produce a C++ iterator. The print all loop structure is quite different. Since we just have a single while loop, because we have our one-stop shop for everything, that next does our advanced read and done. And once we get that value, we just look at that value directly, because in this case, value is an optional. In Rust, this would be a little bit easier because we have pattern matching. So you would instead write, while let sum val equals it.next, and then you don't have to do this to reference, but otherwise it's the same kind of structure. So let's look at what adapting iterators in Rust looks like. Like how do we do map and filter as well? So map iterator is even simpler than it is in D, because we only have one operation that we need to implement. And so all next does is it grabs the next element from its underlying iterator, base.next. And if we have one, then we invoke our function on top of it. And if we don't have one, then we return null opt. And in typical optional implementations, this is a member function that we have on optional, just called map. So in this case, next on map editor just calls base.next.map. And that's about as simple as it gets, right? So we implement next in terms of base.next. We get all of our functionality in terms of the underlying types, all of its functionality. So just one type, just two functions. And again, even the constructor here just constructs, just copies base and fun. So not much work there. Quite easy to implement in comparison. Filter, again, is slightly more complicated, but here we don't have the problem that we had to deal with the reading languages, which is like, how do we actually find the first element to produce, since next itself can just do that. And next is the only entry point. We don't have, we never see values again. So we don't have to worry about any kind of like advertised cost for what calling next might mean. Next itself just does a loop. It returns an element that it finds. So here again, one type, two functions. And now if you're curious at this point to actually see what the Rust iteration model might look like, if we did go all out to implement all of these algorithms in C++ and really do a good job on it, I would suggest taking a look at Tristan Brindle's library libflow, which you can find on GitHub. There's a lot there, so check it out and see what you think. Now, so I call this the Rust iterator model, but Rust is not the only language that does this. Python is quite similar in this respect. Of course, it spells its next with underscores because it's Python, but it's really the same exact kind of model. There's a single function that does everything that eventually fails. In the Rust case, next will eventually return a disengaged optional. In the Python case, next will eventually throw an exception, but it's really the same kind of thing. And even Java is very similar in this case. It also has next on its iterators. The only difference is that while next satisfies the read and advance basis operations, it has a separate function, has next, to do done. And so if you're going to draw a line between all these languages, the obvious line to draw is kind of here, where the languages above the line are the reading languages, the ones that have read as a distinct operation, and the ones below the line are like the iterator languages. And here, this is kind of a little confusing coming from a C++ background, where what we call an iterator is very different from what Rust or Python or Java call an iterator. But we're kind of losing the game of numbers here, since all of those languages call what they do iterator. So I'm just going to give them that name. So Rust, Python, Java, and there are others are the iterator languages. But Java's kind of like the oddball here. It's a little bit different from Rust and Python, and it's kind of worth going through the distinction there. So if we were going to implement filter in Python, it would look very similar to the way that we implemented filter in Rust. The primary difference is that here we get our nice infinite loop, right? So like Andre always says, infinite loops are for speed, except in this case, we're throwing exceptions on failures, so maybe not so much for speed. And so in this case, base.next will eventually throw when we run out of elements, and that's enough for our termination condition. Our job is just to return the kinds of elements that we can. So that's filter in Python. And so you'd think that in Java, it would also look basically the same, since Java also has a very similar contract. Next either returns a reference or throws when you run out of elements. However, we have this extra thing that we need to do, right? We have to do has next. And what do we actually do there? Right? Like we can't like check something, because like next we'll skip it if we do something like that. The only thing we can really do is we have to cache an element, right? We need some kind of set next that tries to find an element that it can stash that satisfies a predicate or not. And so what has next would then do is return true if we either have a cached element that we need to return, or we try to cache an element and we succeed in caching an element. And once we do that, we can go back and we can implement next. And so what next does is like either if we neither have a cached element nor can set one, then we're out of elements, we throw. Otherwise, we have to pull out our cached element and clear out our cache. So this isn't super complicated, but if you look at the condition in next, I mean, that's exactly if not has next. And so that's already kind of like a strange thing to do. Like if you have your model such that the way that you implement next is that if not has next, throw no such element, that's true for every adapter, right? That's just universally the way that you would implement anything. And we can reduce this a bit, and we can add like a nice take operation on our optional that lets us clear it out easier, and that'll come up a few times shortly. But this is kind of weird. It's a weird burden to have to impose on the user to have to provide this has next operation. Since a lot of times you don't actually need to know whether or not there is another element coming. It's enough to just take the next one, and that operation, if you need it, is something that you can actually provide as an algorithm. So in Rust, for instance, we have Peekable. And Peekable is an algorithm that you can implement on top of any Rust iterator that caches an element, right? So we can implement next such that it like potentially peeks, uses an element that we have cached or not. And we can add another function to it called peek, which caches an element if possible. And so like if we need this functionality, if we need to potentially look at an element or just know if there is going to be another element, that's a cost that we can choose to pay for if we need it. Unlike in Java, where we have to pay the cost for has next in every algorithm, whether or not we need it, which is kind of a strange choice. And I'm kind of curious as to why Java went that route. And I suspect it probably has to do with the fact that Java didn't have optional yet, and that exceptions might be expensive in Java. That was the only other option. But it sort of ends up being like a little bit odd as compared to Rust and Python in this sense. So let's go back to this example that I showed earlier, where we had map and then filter, and then I asked, well, how many times is some operation invoked? And we showed that for the reading languages, it depends, right? Like it's invoked twice for every element that matches the filter. But in this case, it's always exactly 6, no matter how many elements match the predicate. And it's kind of worth going through and seeing why that is, right? So from the Rust model, when we get the next element from the filter, that's going to get the next element from the map, which is going to invoke a function. But once we have that element, and we just use it. So when we check the predicate on that element, we're checking it on the value that we already have in front of us. We never have to go back to the map iterator. And when we return that value, we just return that value directly, and the user uses it directly. they don't have to go back to the map iterator either. And so there's only like one touch on every element the whole way down. The same is true for Python. When we get base.next from the filters next, that has to invoke the function. But once we have this reference, we just directly use that reference, and we never have to go back to map. The same is true in Java. There's a lot more code here, but the structure is basically the same. Would we cache an element, that might invoke a function. But once we have that element cached, we're just reading from that element directly. We never have to go back to the map. And so we only invoke this function as many times as necessary. So now that might beg the question, like, okay, so do these languages actually just like offer free performance? Why don't we just use the Rust model? So consider this other example. So this is the same kind of code I had before, except instead of doing a map then a filter, we have a map and then a drop. So drop is an algorithm that skips the first n elements of the range. And now the question is, well, how many times is this operation invoked this time? And so in this model, it's still exactly 6, right? It doesn't matter that we're not looking at those elements. We still need to get them so that drop can skip them to grab the next element. And so that still involves invoking the function. So we always invoke the function. But in the C++, D, and C# world, this is separate, right? Read and advance are separate operations. And all drop needs to do is advance. It never needs to read. So we don't pay the cost of reading in our advance. And so in Rust, we could reorder this, right? In this case, we could drop to and then map. And now our Rust model and our C++ model line up and do for another case. But we're much more order dependent in these languages. You have to be more careful about these kinds of things. So the other question might be, do these languages offer equivalent functionality? So let's go back to findIf, my favorite algorithm in this talk. So in C++, findIf is again straightforward algorithm, straightforward loop. We loop until we find an iterator that matches the predicate, and then we return that iterator. But what we can do with that result is a lot more interesting. So if we have a container, let's say a vector or a list or whatever V happens to refer to, I can look for an element from that container that's bad, and if I find one, I can erase it. Right? This is a pretty powerful idea that we have from the standard template library. So how do we do this in Rust? Well, we kind of immediately have the first problem of what does findIf even return? Does it return an iterator? Well, it can't return an iterator because once we pulled out the elements that we might have that matches the predicate, that element's gone. Like if I would give you back that iterator, you're not going to get that element back again. So that's not going to be a very useful return. I could wrap it in peekable so that you can peek at it again, but that doesn't like work very well either. So the best option I have is actually to return an optional reference for which actual value you found, right? So again, the implementation of this algorithms looks a lot like it did in C++, except we're returning a very different kind of thing. Instead of returning an iterator, that is the first element that matches, we're returning the value that satisfies the predicate. But once we have this value, what do we do with it? Like, if we specifically have a vector, well, we can erase that index by computing the index using this difference because we have this contiguous container, and so that kind of works. But what do we do if we're not using a vector? And now you might ask, well, don't use any container that isn't vector. But that's not really like a practical solution. Sometimes you do need to use things that aren't vector. And so what you end up doing is you write a different algorithm. And I've already shown position once when we were talking about D. And we have to rely on it again in the Rust model. So position returns the number of elements before the element that satisfies the predicate, or a disengaged optional if there is no element. And we use erase at index. And what we have to do is just kind of hope that V is random access. And so if what you're dealing with is a linked list, and sometimes you really do need linked lists to solve a problem, you've suddenly acquired this extra linear time operation to do this erasure when you needed to do it. So that's, it's less than great. This works okay if you only use contiguous containers like vector or slice or something, but not so great once you step outside of that realm. And there's some functionality gaps here as well. So let's look at group by. Group by is a very interesting algorithm because there's a lot of different flavors of group by in a lot of different languages. And in other languages, this also comes up under a lot of different names. So some languages call this partition by, some languages call this slice when, or chunk by, or chunk on. But whatever it is, there's really two main strategies for group by. One is a binary implementation. So for instance, in this case, we take the predicate less than or equal to, and what we do is we traverse the range 2 elements at a time. And as long as that predicate returns true, we group those elements together. So 1, 2, 2, 3, it still returns true. And then we eventually get to 3, 1, the predicate returns false, and then we start a new group. And then when we get to 1, 2, we're back to returning true, so that's a new group. So the result of applying group by in that case is we end up with these 4 groups. But there's a separate approach, which is unary. We take a single projection function, and what we do is we apply that to every element, and that kind of gives us equivalence classes, if you will, the elements that have the same value under that projection. And then we group consecutive elements that project the same. And so in this case, we end up with this set of groups. Also, both of these algorithms are very useful. But the important thing to point out is that the unary implementation can always be implemented in terms of the binary implementation, right? So if I have a unary projection, I can always pass it to group by as just applying that projection to both elements and seeing if they project the same, right? But that's not true in the other direction. So there's no way to take this less than or equal to predicate and come up with some kind of unary function that gives us those same groups. This is impossible. So group by is kind of the more general algorithm. So let's kind of see, like, how would we implement this binary group by in the Rust model? Okay, so we start off with like this, and I'm only going to focus on the inner iterator since I think that's the most important part. So rather than returning a range of ranges, in this case, we're just returning a single range, and we're trying to figure out when we stop, so that the outer iterator has to figure out how to start a new range, right? So we start out by grabbing the next element from our underlying range. And if we run out of elements from the underlying range, then we're done. That's the easy case. If we run out of elements completely, then we certainly are done with this group that we're producing right now. But once we have an element, we have to invoke our predicate against something, right? So what do we compare to? So the first thing that we might think to compare to is to stash a reference to the previous element, right? So we have this prev, which is also a reference, and there will be some check to make sure that, like, we actually have a previous element in this case that I kind of skipped, but we invoke that. But the issue here is, like, so we have 1, 2 different references into the underlying range that we're holding on to. We have prev and we have a current value, and both of them are references. So you can't do this in Rust because of the borrow checker, but you don't want to do this in C++ for a different reason. And that reason is, let's take an aside and talk about getlines. So getlines is an adapter that just repeatedly calls getline on a stream and returns that string. And in the Rust model, this is exceedingly easy to write because we just call getline, and if that continues to return true, then we return our value. And once that fails, then we return null opt. But the important thing to point out here is that we're always returning the same reference, right? We have one string that will potentially get larger as far as capacity goes as we do getlines. But it's always the same string that we're returning. So this is actually pretty efficient as far as range adapters go. But we'll completely break this implementation because prev and val would both point to the same element, and that's bad. We'd always end up with a single group that contains all of the elements. So what we have to do instead is make sure that we actually have distinct values. And the only way to have distinct values is to store a value. So prev is going to be an optional value. And so we need to make sure that if we satisfy our predicate, that we have to stash prev so that we can use it the next time. And the consequence of this is that we're copying every single element, right? Like if you're grouping any range, the only way that we can implement this algorithm in Rust using this model is to copy every element as we go. And that's pretty expensive, right? And if you kind of think about like what this might look like in C++ or D, where in C++ we can just keep 2 different iterators into the range. We don't need to copy elements. In Rust, we would keep 2 different ranges and increment them as we go and popping as we go. But we don't need to copy the values. But in Rust, we do because we have no access to elements once we get past them. So that's why in these languages, you don't see binary group by. So like in Rust and Python, you will only see unary group by, which kind of avoids this problem. But that's not the only algorithm that we're missing. We don't have a JSON binder or JSON difference. or adjacent transform. Those are for the same kind of thing, right? The only way that we could possibly provide this algorithm is by copying every element in the range, which is expensive. We don't have sort. You need some kind of way to talk about the elements, and the Rust iterator model doesn't provide it. The only thing you can sort in Rust is a vector or a slice, which is what in C++ we call a span. But it's still useful to be able to sort things that aren't simply vector. So consider that we have a vector of strings and a vector of ints, and we might want to sort them mutually. So we want to sort the names by the ages, and so end up with both containers being sorted in increasing order by age. And in C++, we can do this. We can construct a zip view of names and ages, and that resulting view will still be random access. And we can sort any random access range. And this works and is efficient. And as a result, we end up with ages being 27, 31, 37, and the names being Steve, Jane, Bob, as expected. This simply isn't something that you can do in Rust. The model doesn't let you provide that. Similarly, there's no way to provide slide. So in other languages, this might be called windows or even tuple windows. So slide is an algorithm that takes overlapping ranges of your original range. And again, the only way to provide that is to copy every element. So if you look at the specification of slide, it requires your element to be copyable because the algorithm has to copy it. That's a lot of copies that might end up happening. Because you can't access multiple elements at a time, you only get one. There's no sub-range kind of algorithms that you can provide. So there's no search, there's no mismatch, there's no find n. Similar, there's no way to do lower bound or upper bound or equal range or binary search, any of these kind of algorithms that involve random steps, because there's no random step. The only way you can only step one element at a time. Because you can't visit multiple elements at a time, there's no way to do next permutation or pre-permutation, which might need to go back and forth across the range many times. You can't do that. There's no stable partition, and especially depressing to the C++ algorithms community is that there's no way to rate rotate. That's definitely not a rotate in Rust. You can provide partition on a double-ended iterator, but partition returns an index. Like a lot of these algorithms, we can't return an iterator. The only thing that we can return is how many elements satisfy this predicate, not kind of where the dividing line is. So that's still useful, and it's still quite a useful algorithm to have, but we kind of miss that connection with, well, okay, well, what if I want to do more things with that iterator on either side of the partition? And likewise, we obviously don't have min element, max element, or min max element, because like these algorithms don't even make sense at all in this model. It makes sense to have min and max because you can return that value, but it's not really meaningful to return the iterator that refers to the minimum element. And sometimes those algorithms come up and are very useful, and those things just don't have any meaning in this model. You just can't provide them. That said, like if you don't need to do these things, then like me presenting all these algorithms that you don't need to use, or maybe you only need to use on vector, it doesn't seem like a super compelling argument, and that's fine. That maybe that's the model for you. And like I mentioned, you can check out Tristan's library and maybe start using it. So if we put Rust on the graph I showed earlier, I would put it down here, right? This is obviously much simpler a model than either what D or C++ are able to provide. If anything, this graph really does a poor job of conveying simply how much less complex the model is and how much easier it is to think about how to do things in Rust compared to the two languages. But it also offers significantly less functionality. The lack of iterator to container cohesion limits the kinds of things that you can do in that language unless you're strictly dealing with vectors. And there's a lot of algorithms that just can't be provided generically, which really hurts. And Python kind of fits in the same place as Rust, but I thought it was really worth calling out Java here as being on the clearly wrong side of the complexity functionality curve. Because they have to provide has next, it makes the implementation more complicated and less performant while also providing no additional functionality, which you could provide with an algorithm on top of the model at much less complexity. So I just wanted to call that out. But in the end, I feel like all three of these languages, C++, D, and Rust, are really like on this efficiency frontier. They provide different trade-offs for the models, but I think they each do a good job of like addressing the problems that they intend to solve. And so, Rust didn't necessarily set out to solve this container versus algorithm duality, and so it just doesn't. It doesn't solve those, and that's okay. It's still a very useful model that a lot of Rustations will sell you as far superior, and it's certainly easy to sell as for being less complex until you run into those cases where I kind of wish I had an iterator here. I kind of wish there was something else that I could do. And so that's kind of what I think about these things. Sometimes I also wish that I had the Rust iterator model in C++. Sometimes I wish that find_if returned a range instead of an iterator, as it does in D. And sometimes I'm kind of happy with where we're at in C++. So maybe this is kind of like a letdown place to end up for the people that were kind of looking forward to me bashing one language or another, which I'm not really doing, with the exception of Java. But that's kind of the conclusion that I draw. So I see there's a bunch of questions that I didn't get to at the end, and so I'll kind of open up if anyone has questions at this point. So some of the questions are like, are there utilities like Boost Iterator or Boost Iterator Facade that could decrease the complexity of writing new range adapters? Like, can we provide library solutions to this complexity problem? And I'm kind of torn about the answer to that question. I think the answer is really like yes and no. So yes, so there's a new Boost library that Zach Lane wrote recently called STL Iterators, or I'm sorry if I'm getting the name wrong. That makes it a lot easier to write an iterator. And if you look at the range v3 implementation, there's a lot of different adapter classes that library uses internally to make the implementation of these types much smaller. So if you look at the implementation of transform in range v3, it's actually less code than what I showed on this slide here, even though it does the same thing. But where I say I'm torn about it is that I've written a bunch of range adapters at this point, and even though they're super verbose, because like I've only shown support for forward iterator in this case, and there's 2 more operations that you have to write for bidirectional, and there's something like 6 or 7 operations that you have to write to support random access, and plus your Sentinel also has to support operator minus to be a size Sentinel conditionally. But I find that it's kind of nice just to write all of them. It's kind of rote, and there is some boilerplate, but the end result is that it's much easier to read because it's all kind of in front of you. So I don't really know what the right trade-off is between simply writing all the operations and using some kind of adapter or facade or some kind of CRTP utility to vastly reduce the number of operations that you have to write. It's certainly more error-prone if you have to write 20 functions than you have to write 4. But there's also something nice about having someone reading your library that isn't familiar with those adapters, being able to very easily understand. And obviously the big win from D and especially Rust is that like you don't need any of those libraries, right? Like there's no reason to adapt any algorithm because there's actually no repetition anyway. Like in D, pop, front, advanced, that's it. Those are all the functions, right? There's no like, oh, we have pre-increment and post-increment, and we have pre-decrement and post-decrement. Like that's just not a thing in D or Rust. So those are easier. All right. Well, no, thanks for coming. I hope you all enjoy the talk. I'm going to be in the Gather answering questions directly if anyone wants to bug me. Hope you enjoyed it. All right. Take care.